Hello everyone, I'm Akihiko Kasagi from Fujitsu Laboratories Limited. The title of my presentation is Efficient Technique for Large Millibatch Challenge of DNNs Training of Large-Scale Cluster. Motivation. Recently, deep learning development is growing rapidly. The computational cost of deep learning grows beyond Moore's law. Thus, single processor power is not enough to support the deep learning development. So we need empowerment by thousands of processors. Here, I'd like to explain the large Miwa challenge. In this challenge, we compute a fixed problem-size deep learning process with many GPUs. In distributed parallel deep learning with data parallelism, throughput increases linearly according to the number of GPUs. The size of Milibachi also increases according to number of GPUs. However, validation accuracy decreases when we use a certain milliwatt size. This is a unique problem on the large-scale deep learning. Next, I'd like to explain the position of our study. Related work proposed several methods in order to prevent loss of accuracy, such as LARS, level smoothing, warm-up, and so on. Today, we propose a new method which is compatible with them. Our contribution is preventing loss of accuracy and enables huge milliwatt size. And our method enables many GPUs and accelerates large-scale deep learning. Let's consider why low accuracy in large milliwatt challenge. Generally, we use SGD updates in deep learning. This method is one iterative method. Thus, the number of iterations is very important to converge the neural network. If we use the large milliwatt size, the number of iterations becomes small. This is because the number of iterations is based on the size of the dataset and milliwatts. For example, ImageNet dataset has 1.28 million images, and if we use 81,920 milliwatt size, the number of iterations in an epoch is only 60. This number is too small to convert the neural network module. So the small number of iterations cause loss of accuracy. Related works propose several update methods of weights with a small number of updates. In this study, we focused on the batch normalization layer used in convolutional neural network. This layer has two values of mean and variance. In the training, this layer obtains the mean and variance of current milliwatts data to normalize the input. Then, batch normalization layer holds these values and accumulates them using moving average during training. These accumulated mean and variance are used in testing. So this layer uses them as the sample of mean and variance. If the total number of iterations is small, it is difficult to converge to appropriate mean and variance values. This leads to the loss of accuracy. Next, we consider the effect of data augmentation on the batch normalization layer. Data augmentation is a popular method and creates various images to improve the validation accuracy. For example, clipping algorithm cuts out the images from the original images. Then, the mean and variance of augmented images are different from the original image. So the batch normalization needs more iteration in order to converge the mean and variances. Here, we proposed our method final polishing. This method turns the data augmentation off during training. The turning off is performed near the end of training in order to benefit from data augmentation. This graph shows the relationship between turn-off epoch and accuracy. Horizontal axis means the timing of turning off the data augmentation, and each point means a validation accuracy of less than 50 after 90 epoch training. As shown in this graph, turning off just before the end of training can achieve both the data augmentation effect and the batch normalization convergence effect. In addition, we investigated the effect of turning data augmentation off. Here, we prepare three training approaches: baseline, extra forward, and final polishing. Baseline is naive approach and trains the neural network in 90 epochs with data augmentation. Extra forward approach applied one epochs forward process to baseline. Because extra forward did not perform backward and update, extra forward did not change the model from baseline, except for means and variances in the batch normalization. Comparing with the accuracies between baseline and extra forward, this result shows the mean and variances did not converge at the end of 90s epochs. Final polishing is our proposed approach, and this result shows that turning data augmentation off during training is more effective. This is because the turning off affects not only batch normalization but also model update. Next, we evaluated our method in large-scale cluster. We used ABCS supercomputer by ICE. We trained ResNet 50 using 3072 GPUs of Tesla V100. And the software configuration is below. This is the experimental result. We measured learning time of 90 epochs training using 3072 GPU. Then the Miwa size is 86,016. We searched the appropriate parameter of turning off epoch beforehand, and we turned data augmentation off at 85th epoch. In addition, we used LARS, label smoothing, and warm-up techniques to prevent loss of accuracy. And we used clipping and mirroring algorithm as data augmentation. In this graph, the green line denotes the learning rate and the red line denotes the validation accuracy. Finally, the validation accuracy reached 75.96%. Also, the 90 epochs training completed in 62.1 seconds. This table shows the comparison with other works. Our final polishing enables 86,060 milliwatt size. This large milliwatt size makes GPUs run more efficiently and accelerate. Also, the challenge was accuracy, and our method prevents loss of accuracy. In this presentation, we proposed final polishing. This method turning off the data augmentation during training and helps to convert the mean and the variance of batch normalization layer and prevent loss of validation accuracy in large milliwatt challenge. This method is compatible with other techniques such as LARS and label smoothing. In addition, it enables large milliwatt sites and many accelerators. In the experimental results, we measure running time of 90 epochs training of less than 50. We used 86,016 milliwatt sites and 3072 GPUs, and completed the training in 62.1 seconds and achieves 75.97% validation accuracy. That's all. Thank you for listening.